Okay, so our corollary, um, well, the solution of the integral equation obtained in the last theorem um, belongs to um, let's say the solution u to LQ minus TT LP1 Rn. Okay, for all pair PQ that satisfies let's say star, it will be this is a star. What are the same conditions that we have for the corollary of the when we work out the local theory for L2? Um, so then we will have the solution in this space, and moreover in this space the solution depends continuously on the initial data, the same that happened for L2 again. Okay, so now the theorem for the critical case, alpha equal to n plus 2 over n minus 2 for n greater than 2 in H1, given u naught in H1, there exists a t greater than 0 and a unique solution in minus tt with, well, u is going to be in minus tt H1 Rn of intersection RR minus TT L rho 1 Rn, where R is equal to 2n over n minus 2, rho is 2n squared over n squared minus 2n plus 4, and one rho. This will be defined as well, as we did before, 1 minus Laplacian of minus 1 half L rho Rn. Okay, this is with the norm f. Well, in this case it will be 1 rho equal to the norm 1 minus Laplacian when half f rho, just like we did before. And well, like always, moreover, for all t prime that is less than t exists a neighborhood w of u naught in H1 Rn such that the function f from w to the set, all the set, the function that takes the initial condition to its solution, yes, Lipschitz. Okay, this is the theorem. Okay, so first of all, we observe that, well, once again, the pair R rho, that is this, satisfies the conditions of the corollary. Okay, and we will bound first this integral the gradient x u alpha minus 1 u. Okay, r prime rho prime 1 over r prime. Well, we will bound this using Helder. C multiplied by the integral 0 t of well, gradient of u r rho 1 over r 0 t u of minus 1 all b 1 over l. Okay, here we're using that 1 over r prime is equal to 1 over r plus 1 over l. This will be less than equal than c integral 0 t gradient x u r rho 1 over r, and now we will take out the exponent, obtaining norm u l of minus 1 b of minus 1 1 over l, and now we're using that 1 over rho prime is equal to 1 over rho plus 1 over b, and we can say that 1 over r plus 1 over r prime is equal to 1 over rho plus 1 over rho prime, and all is equal to 1. Okay, so using that alpha r rho, okay, so let's put it like this, is equal to n plus 2 over n minus 2 comma 2n n minus 2 2n squared, well, n squared plus 2n plus 4. We have L alpha minus 1 equal to r, and B alpha minus 1 equal to 2n squared over n minus 2 squared. Recall that have B alpha minus 1 here and alpha minus 1 here. Okay. Okay, so now we're going to use the Gagliardo Nirenberg inequality. Okay, so this is the inequality in the general form that the dx alpha f in the norm p is less than equal than c, and then the sum of the norms of the derivative q, so the exponents theta and 1 minus theta, as we did in the interpolations theorems, that satisfies this. But we're going to use something that is near this result. This is that if f is in HS and then f is in LP, we will have this inequality when S satisfies this. Okay. So using Gagliardo Nirenberg's inequality, we will bound u in the norm B alpha minus 1 with norm u 1 rho. This will be equal to C u rho plus gradient x u rho. Okay. So now, as the same way we did in the last theorem, we will have that for any epsilon positive, x is t greater than 0, such that, so what we want to bound is, recall phi, the integral equation, r1 rho, okay, dt 1 over r. This will be less than equal than c 0t phi r rho dt 1 over r plus 0t. Now we have the gradient of x of phi r rho dt 1 over r. And as we did before, we will bound this by c epsilon and this c plus absolute value of lambda 0t u r rho dt 1 over r, okay, plus c lambda 0t gradient x u r rho dt 1 over r multiplied, this will be multiplied by, let's put it down here, integral 0t of u r1 rho dt alpha minus 1 over r, and this all will be less than equal than c epsilon plus c lambda integral 0t of u r1 rho dt alpha over r. Okay, now on the other hand we have that the supreme COT naught phi u minus EIT population u naught, it will be in the norm 1 2 less than equal than c lambda and integral 0t of u r1 1 rho dt alpha over r. Okay, so now we redefine the set u1 ta, again the b's that are in c COT H1 Rn intersection LR L rho 1, such that we have that this norm supreme BT minus ET population u naught 1 2 plus integral 0t v r1 rho dt 1 over r is less than equal than a. Okay, so using this we know that we have for all epsilon greater than 0 t positive, such that u is E1 TA as we defined. Then we have that phi ut norm is less than equal than c epsilon plus c lambda a to the alpha. So the rest of the proof follows an argument used previously, okay, and then we have a corollary that there exists an epsilon greater than 0 depending on lambda and n, such that if u naught is in H1 with the gradient of u naught greater than epsilon, the results of the theorem will extend to all time intervals. So u will be now in time r, all intervals H1 here again, are around L1 rho.